Hello, students. I think we should try to prove this identity combinatorially by showing that the left-hand side and the right-hand side both count the same thing, just in different ways. So what do I have here? I have a bunch of Stirling numbers, and on the right I have a sum of these Stirling numbers, but each one's multiplied by a binomial coefficient. And on the left I just have this one term. Now which side's easier? Well, probably for most of you the left side is easier. It's just got the one term. And I'm noticing I see an n plus 1 here, but I don't see any n plus 1s there on the right. So that might be giving me a little bit of a hint right there. Maybe this is telling us, hey, on the left, I have these n plus 1 objects. Or we could think of them as just the numbers 1 through n plus 1. They are distinguishable. And I'm dividing them into k plus 1 indistinguishable, non-empty subsets. Okay, that's what I have here on the left. But on the right here, I have this big jumble. Okay, but all of these tops start with n's, and there's no n plus 1s here. So maybe I could say, okay, is there a way to think about how I could split this up by deciding where the n plus 1th element goes? You know, we have this n plus 1th element. So that n plus 1th element, well, it's got to go with some group. And based on that group, maybe I could break things down. Okay, now, you might be saying, hey, sound like you're trying to spark some insight, but I still don't get anything yet. So let's try to look at an example. Maybe we'll start here. Let's try this one. So we're letting n be 4 and k be 2. N is 4, k is 2. Okay? Now in this situation, what do I get? Well, I get 4 choose 2, and that Stirling number. And then I get 4 choose 3, and that Stirling number. And then I get 4 choose 4, and that Stirling number. And obviously we couldn't continue if we wanted to, because we couldn't take more than 4 out of 4 there. Okay. So let's think about this. I just said we're picking out that n plus 1th object because we don't have any n plus 1s there on the right. So think about maybe, hey, I want to split the numbers 1 through 5 up into subsets, but I don't know where the 5 goes. So maybe I could break things down based on where the 5 goes. Okay, well, aside from where the 5 goes, I have the other stuff, and the other stuff has to go somewhere as well. So notice that when it comes to the other stuff, if I look at this as being the other stuff, I'm splitting these into 2 subsets. So I can think about it as, okay, I have one subset where the 5 goes, and then 2 other subsets. Okay, that's a start. That's a start. That'll give me the 3 different subsets I need. Okay, and I don't know which of these terms is easier. It might depend on the way you're looking at it. But let's try to look at this case. We could say, okay, I want to put the 5 somewhere, and this is maybe trying to tell me where things go. Well, here I'm choosing 4 elements out of 4. Well, that would be everything that's left that's not 5. And what am I doing? I'm splitting those 4 into 2 different subsets. This would correspond to the 5 being maybe alone. So I could think about this as the 5 being alone. And this could be all the different ways that I could split the other 4 into 2 subsets. So namely, I could do 1, 2, 3, 4, 5. Or 1, 2, 4, 3, 5. Or 1, 3, 4, 2, 5. Or 2, 3, 4, 1, 5. Keep in mind that even though I'm drawing these in order, they're not in order. I'm not like 1, 2, 3, 4, 5 is not any different than 1, 2, 3, 5, 4. But I could always write them like this. I want to write the 5 on the right to just emphasize that this is the thing that we're sort of splitting up. Okay, but I also have the 1, 2, 3, 4, the 1, 3, 2, 4, and let's see, the 1, 4, and 2, 3. All with 5s. Okay, well now 4 choose 4 is 1, and it does turn out that the Stirling number of S42 happens to be 1, 2, 3, 4, 5, 6, 7. So this would represent that. But okay, what about this? Now I'm choosing 3 of the possible numbers to split into 2 groups. So let's start off by taking a look at what that might look like, right? I could say, hey, I'm going to take 1, 2, and 3. So I could do that, 1, 3, and 2, or 2, 3, and 1. Okay? And then everything that I didn't take, I'm just going to stick that together with 5. And of course, I didn't have to choose 1, 2, and 3. I could have chosen 1, 2, and 4. So I get 1, 2, 4, 1, 4, 2, and 2, 4, and 1. And here I'd get all the 3 5s. And so on, and so forth. So this, I'd have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, now what about this one here? For this one here, I'm choosing 2 things to split up into 2 groups, and everything else goes into 5, with the set that 5 is with. So let's say I could split 1 and 2. There's only one way to split 2 elements into 2 groups. They're each in one set. So, and everything else goes with the 5. Okay? But I could also have the 1, 3, 2, 4, 5, the 1, 4, 2, 3, 5, and I could have the 2, 3, 1, 4, 5, the 2, 4, 1, 3, 5, and the 3, 4, 1, 2, 5. Okay, now remember, the 5 has to go somewhere. So either the 5 goes alone, and what we have to do is we have to take all the other elements and split them into 2 groups. Or the 5 is not alone. It has 1 friend. That means I have to pick 3 of the other elements, and I have to split those 3 elements into 2 groups because I need 3 total groups. So these are all the ways. Of course, there's 6 more here. 6 more. Because I'm only doing the first 6 here. I didn't feel like bothering you with writing that out. But these are all the ways that I could give 5 1 friend to be with. 5's got 1 friend it can be with in these ways. And this one, in this situation, I'm saying, okay, now 5 could be with 2 friends, and I have to split, well, the rest up into 2 subsets. I have to have at least 2 elements to do this. I can't get any smaller. That's why I don't have a 4 choose 1 to the left of that, or a 4 choose 0 or anything like that. So this seems to be giving me every single way that that I can actually split these 5 elements into 3 sets. And if you just actually look at the numbers here, I get a 6 times 1 here, I get a plus 4 times 3 here, and here I just get the 1 times 7. So, and here you actually see all of this. And this does indeed add up to, this is the hard part, 6 plus 7, 13, plus 12, 25, which actually is this Stirling number. Okay, so what this is doing, and now I can see it in the general case, what we're doing is we're saying, hey, the left-hand side counts the number of ways I can split all the numbers from 1 to n plus 1 up into k plus 1 sets. And on the right-hand side, what we're doing is we're splitting this up based on the number of elements in the set that gets n plus 1. If n plus 1 is by itself, well, we choose everything else and we split it into k sets. If n plus 1 has 1 friend, well, then I choose everything else but 1 friend, and I split those up into k sets, and so on and so forth all the way down. So the right-hand side is the number of ways you can compute the left-hand side based on how many different elements share a subset with n plus 1. And that is a way to do a combinatorial proof of what might at first seem to be a sort of intimidating identity.